Welcome to the third video in my Pinzgauer EV conversion project. In parts 1 and 2, we took a look at the first attempt at this conversion and started diagnosing and addressing some of the problems with the mechanical aspects of the drivetrain, in particular a leak and a bad vibration. If you remember from the second video in this series, we already rotated the motor to properly orient the sump, which we could test without designing any new parts. But now we need to address the vibration, which we diagnosed but couldn't fix with parts on hand. To address the vibration, we've got three things to do. The plan is to raise the motor, which reduces shaft offset. We're going to synchronize the Cardan joints properly, which is trivial. And we're going to design a new spline adapter with a retainer of some kind. All right, let's get into this creative engineering project. The first thing to figure out was how much to raise the motor. In my case, I decided I wanted to straighten the shaft as much as possible, so I would raise the motor the exact amount to put its output shaft at the same height as the input shaft to the transfer case, which turned out to be 63 millimeters. I also wanted to move the motor as close to the torque tube as possible to reduce the horizontal offset as much as possible. But the diameter of the motor limited that move to about 5 millimeters before the motor housing encountered the torque tube. So up 63 mil, over 5 mil. Which brings us to CAD. The guy who started this conversion had all his drawings in Onshape, an online CAD program, and he gave me access to the project. I've used CAD programs, but in very rudimentary ways, and what is available today was eye-opening. Thankfully, in spite of the fact that this business owner really didn't need to, since his business didn't even exist anymore, he helped me get up to speed with modifying the rear mount part. It's always amazing to watch an experienced pro do something when you're coming at it for the first time. And by moving the mount holes to their new locations, the part magically deformed itself to accommodate. Literally in under an hour, we had a new prototype drawing. He gave me a contact who would 3D print this in plastic and send it to me for a test fitment. And a few days later, I had a part I could try. I bolted it on and found two small places where the motor and the mount encountered each other. I cut the plastic where it had fitment problems until the part fit well, so I could fully verify the rest of the fitment. I was able to communicate with a screenshot of the CAD where the conflicts were. He made a few changes, and I ordered a second printing of the part, and it arrived in the mail a week later. This one was a perfect fit. One final tweak to make it easier to get my tools to the spline adapter bolts, and also adding some voids for weight reduction, and it was time to get this machined. The business owner connected me with the shop that made the mounts initially, but I randomly discovered during this project that I have a friend whose family runs a machine shop, and he said they could make these parts. Well, that was an easy decision. A few weeks later, the part arrived, already anodized, and it, too, fit perfectly. So at this point, I was feeling pretty hopeful and optimistic. Albeit with help, I had managed to bring this new part into existence, and it fit just how I wanted. And this is when I learned that the guy who started this build had found a new job and couldn't spare any more of his time. So the new front mount was 100% on me. To refresh, here's what the front mount looked like when I got the truck. And you'll remember that we had to rotate the motor to put the sump at the bottom, and we just raised the motor 63 millimeters. So this part will need to be heavily modified. And to do that justice, and because it really is a topic that is meaty enough to stand alone, and because I don't want this video to be too long, I actually splint that modern CAD and 3D prototyping video out separately, which I'll link here, and also at the end of this video. It takes you completely through the design and build process, at least the one I used. I think it's worth a watch. Which reminds me, if you're enjoying this series, make sure to like and subscribe so you don't miss any of it. But yeah, it got made, and here it is installed, and it fits great. And now on to the spline adapter. Alright, so here's the motor output shaft. I decided to use this groove here behind the spline to retain the adapter. Despite an earnest search, there is no specification in any manual I could find, no CAD drawing available, and no response from the manufacturer about the measurements for these grooves. So using calipers, I just measured them as best I could, and unfortunately encountered what seems to be mixed metric and imperial dimensions. For example, the groove measures exactly 3/32 of an inch wide, and the shaft is exactly 22 millimeters thick at the bottom of the groove, and the groove starts 24.5 millimeters from the end of the shaft. So I guess if we design a flange to be flush with the front of the shaft, we can drill two 3 32nd-inch diameter holes, 22 millimeters apart, 24.5 millimeters from the face of the flange, and hopefully slide cotter pins through those holes, which will slide into the groove and retain the adapter. Thankfully, I started working on this part before the front mount, so I still had help. The business owner did his CAD magic to modify the existing part, and I ordered a 3D printed plastic part so I could do a fit test. And it fit great. The cotter pins even slid through the holes exactly right. The only problem was that the fit for the spline itself was a little tight. I could bang the plastic part on, but this is too tight a fit for a metal part. So I found the spline specification in the Remy HVH 250 manual. Actually, I found 2 specifications in 2 versions of their manual. But with this info, I could tell my friend to machine the part as per the step drawing, but use the provided involute spline specification for the spline itself. And they made the part exactly as I asked, and the spline didn't fit quite right, and it took some months to get this right. Alright, so today we are going to get our spline onto the motor shaft. This has been quite a battle. The one that came with the truck was this one, which was actually the second iteration of the adapter that was tried by the guy who built this for me. Now these don't really fit super well. They go on, but they kind of jiggle. As you can see, they kind of jiggle, and it's actually printed metal, so like being part of the drivetrain is maybe a little sketchy. And in fact, this was the one that was on when I picked it up, and in fact this one kind of goes on okay, but it got chewed up on when I drove it home because the metal I think is a little soft, and also it didn't have a retainer. So the drive shaft, when it was mated to it, when it moved, it chewed up the metal. So I decided to have, it's a little, like I said, it's chewed up, so it's kind of stuck on there. So I decided to have one machined out of actual hard metal. And this is EN19T, an engineering steel used in this type of application. The first one that I had made, based on the specification from the manufacturer of the motor spline, went on and it jiggles like this. You can hear it, right? You can kind of see it too, jiggling. So that wasn't good. We actually tried 2 different specifications from the manufacturer of the motor for that spline. Neither of which worked, but I had this 3D printed guy, which fits really nice. Actually, so nice that if you made a piece of metal that was exactly like this, you'd have to it wouldn't slide on easily, and if you'd have to heat it to get it on and cool the shaft or something. So what I did was I asked the machine shop to treat this as a press fitting and duplicate it out of metal, but make a slip fitting to this actual measurement. So after having done that, we ended up with this perfectly machined part that just goes on here. It takes a little bit to find it. But, oh yes, it goes on there, and there's no play. It's the best. And this will fit right on here, and you can see I've got the drive shaft there. It's gonna hook up. Right now I've got the drive shaft tied up so that it doesn't fall apart, because this spline here slides past itself, so that as things shake and stuff, it doesn't, the drive shaft can expand. And yeah, today we're gonna stick that on. So these are the cotter pins I was talking about. They're just I had those holes machined to 3/32, but it's too tight, so we're using 5/64, and those slide right into the holes. And this is flush. Yeah, that's better. Perfect. Okay, now it's retained. And the other guy. Perfect. Okay, now those guys are in there, and this is retained, and we can go ahead and mount the mount the drive shaft. You've got a Cardan joint here. Let me turn that a sec. You have a Cardan joint on that side there, and a Cardan joint on this side. These guys need to be parallel, and they need to be exactly in sync. Otherwise you get a vibration, because this is not a constant velocity joint. Now, in the comments section in the first two videos, it seemed like everybody knew that these guys needed to be synchronized properly, but some people said 90 degrees, some people said 180 degrees, and I did a bunch of research and am including the links to the videos I found most helpful in the description. I'm pretty sure I got this right, but here's the thing. Any vibration from being out of sync here will show up only when the vehicle is in motion. It doesn't cause a shake in the drive shaft itself. The vibration from out of sync Cardan joints is due to the fact that the driven shaft, which is connected eventually to the wheels, is speeding up and slowing down in each turn of the drive shaft, which symptomizes as rapid changes in speed of the wheels and that terrible shaking. All right, so let's finish getting these bolts in. We got them all on there. So now it's a question of tightening it, and I've got this access thing here. I felt very clever when I did this, so that's kind of cool. But yeah, that'll allow me to do this, and then I can hold that with. Is this the one? It is. Okay. All right, so our drive shaft is attached, and I'll torque it down properly in a sec. There you go. That's been here for a few months while I was waiting for that part to come in. And right now, obviously, you can tell that it's in neutral. So just to spin this in neutral and see how much the shaking is reduced, I'm very excited to see. Like, it seems way better already. So we'll see. Now, I'm about to spin this up, but stay tuned, because right after I spin it up, something electrical is going to break. And even as I post this video, I'm trying to get that figured out. The most notable change is that I can no longer talk to the BMS. For what it's worth, this has an Orion BMS original 144 in it that I used to be able to talk to with the CAN adapter. And I can still talk to the inverter, a Cascadia Motion PM150DZ. At this point, I was elated. The vibration seems like it's gone, and the accelerator pedal is working nicely. And now we're about to hear some contacts engaging and disengaging. And that's it. I tried disconnecting the 12-volt battery to see if resetting one of the components might fix it, but no change. And it's so weird because I literally drove this thing 60 miles without an electrical problem. Anyway, my next video is hopefully going to be about how I diagnosed the problem with the electrical system and fixed it, and some road testing. So don't forget to like and subscribe so you won't miss that. It is going to be super fun driving this thing around again.